Hey everybody, Mr. Bells here again. The video that you're going to see right now is for data analysis. It's on things called log laws. So logarithms, again, are what we are going to use to be able to convert between exponential equations, which have difficulty solving, and basically allows us to take big numbers, giant numbers, and scale them down to something that we can work with on a much smaller basis. Okay, so again, different things like sound intensity, which the difference between, say, what a human can hear and what a dog can hear, or between a jet taking off, very quiet whisper. The sound intensity varies by, could be over 100 million. So what we do is we use a logarithm of that number and convert those numbers into something smaller. So like, I'll give you a quick for instance. With an earthquake, the Richter scale is used that way. If there's an earthquake that has a scale factor of 7.2 on the Richter scale, or a value of 7.2, and another one that has a value of 4.2, you're like, man, that's not that big a difference, right? 7.2 to 4.2. Well, it really is that Richter scale has been converted logarithmically into smaller numbers so that they're more comprehensible for us. But in actuality, if you think about it this way, 4.2 to 5.2 is 1, 5.2 to 6.2 is 2, and 6.2 to 7.2 is 3. So it's really 3 levels. And the way logarithmic scales work is that each one of those levels is a power of 10. So I'd be 10 to the first, or 10 times bigger for each increase of 1, or 10 to the second, or 100 times bigger for each increment of 2, and 10 to the third, or 1,000 times bigger for an increment of 3. So what that means is if you hear that there's a earthquake that has a 7.2 compared to one that has a 4.2, that means the force of that earthquake is really 1,000 times more powerful for the 7.2 than the 4.2, because again, the Richter scale is converted into a logarithmic scale. And there are several different logarithmic scales that we use to be able to do that. Okay, so here's some log laws, some properties of logarithms that exist that are going to be a little freaky. Just trust me on it, take good notes on it, and follow along. They all do work. But yeah, they're gonna, seems a little odd. Here you go. So, first one is this, that the log of a product of two numbers is equal to the log of their individual sums. So like if I wrote log of 24, I could also write that as the log of any number plus the log of any other number, as long as those two numbers multiply together to get 24. So I could do log of 4 plus log of 6. And that's true, that the log of this product, 24, is equal to log of 4 plus log of 6. And I'll show you that real quick on your calculator. So here we go. Go ahead and turn it on. So I'm going to do log 24, enter, and I get this number. Give you a little focus on that. And let's do this, log 4, make sure you close parentheses, so it's just doing the log of that 4, plus the log of 6. You can see that they're the same number. Well, what are other factors besides 4 and 6? Well, how about 2 and 12? So log of 2 plus the log of 12. That is true. Now this is going to be really freaky, but it's also true that I could do the log of 48 plus the log of, and then I want you to think about that and be like, whoa, is that really possible? Yes, we can do log 48 plus log 0.5, because 2 times 12 is 24, and 48 times a half is also 24, and it can work for any of these different examples. Okay? So, I could also do it like this. I could say that it's the log of 2 plus the log of 2 plus the log of 2 plus the log of 3, assuming that whatever base this is right here is the same on all of these ones as we go along. Excuse me. Sneeze, sorry. So log 2 plus log 2 plus log 2 plus log 3, because 2 times 2 is 4, times 2 is 8, times 3 is 24. So that's a way, what we would say, if I go this direction, I would, this log number 1, I would be expanding. And if I went the opposite direction from a whole bunch of logs to an individual log, I would be what we call condensing. So that's the first log law, and that's true on every logarithm, assuming that they all have the same base. So let's do this one. So let's say the log of 10. I'm going to say that if I can write this as a quotient or as a fraction, it would work like this. So that's log, let's do 20 minus the log of 2, because 20 divided by 2 is 10. Could also say that it's equal to the log of 40 minus the log of 4. Remember, just keep putting all of these suckers in parentheses as we do it, closing them, and you can check any of those things. So that's log law number 2. And it says that you can take any number that you can write as a quotient, an integer over an integer. We can do that with subtraction, okay? Now, I want to make sure that we're clear on this. This is not the log of 20 minus 2, right? This, nope, bad, 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 nope, can't do that. It's got to be 2 separate logarithms, the log of a number minus the log of another number. Okay, so this is the one that's really important for how we're going to use things, because this, when you see that variable upstairs, is an exponential function, and now you see that variable downstairs, it becomes a linear function. We don't know how to algebraically solve this, but we do know how to algebraically solve this, and that's what makes logarithms so flippin' amazing. Okay, so what I talk about here is this, is that if we have a log of a number raised to a power, this power is pretty cool. Its ability to be able to remove the exponent and change it into a multiplication problem. So the y that was up here, see this imaginary y that was up there? It actually can come down right in front, and I call this the log-ride law. And the log-ride law basically says, just like if you were at Cedar Point or up at the one over in Muskegon, Michigan Adventures, if you're on the log, right, and you're riding on it, you can go from the top of the thing all the way down to the front and make a big splash, okay? Now, I want to be clear on this. You cannot do this. You can't just take a 2, this does not equal to x. You can't just take an exponent and bring it down in front of something. The only way you can do it, is if you have the log with it, and then the 2 can come down in front. So log x squared is equal to 2 log x. And I'll kind of give you a little breakdown as to how this works. Let's see if this makes sense to you. So I'm going to do the log of 8. We know that log law number 1 says that I can rewrite this as log 2 plus log 2 plus log 2, because 2 times 2 times 2 is 8. Is that good? Now, if I did this, let's see if you buy this. 8 is the same thing as 2 to the 3rd power. Is that good? 2 to the 3rd power. 8 and 2 to the 3rd, that's the same thing. Sorry, I got to put that on the outside. Not 21 to the 3rd. Let me just rewrite that so you don't get messed up. And over here, a log 2 plus a log 2 plus a log 2 is 3 of those log 2s. And now you can see the only difference between this expression right here and this expression right here is the 3 is down in front. And that's why log law ride works for us. Okay? Next one, this is called the change of base law. So let's say that I had this, log of 27 base 3. Actually, let's not do that. Let's do something that has something different in it. Let's do log 25 base 5. Okay, so you know, if I do this, that I cannot put in log 25 into my calculator, right? Because that's implied to be base 10. So what happens when I have a base that's other than the base that I want? Well, if you have this nice calculator right here, you can go to math, and you can go all the way to here, A, log base, and it allows you to change it right on there. But what happens if you don't have that nice calculator? Because some of the calculators don't have that. Well, then this is what you need to do. It's true, right? We know, if we're trying to evaluate this, we know that, doing the baseball analogy, right? 5 to what power equals 25? 5 to what power equals 25? We know that the answer needs to be 2. That's just what works, okay? So how do I put that into my calculator? Well, this law says that if you have a base other than 10 that you would like to do it with, you simply need to do the log of that number over the log of whatever the base is. So log of x over log of y. So then I would write log of 25 over the log of 5. And remember, we already know, because we can do that number easily, it's equal to 2. So if I do it here, watch log 25, close parentheses, divided by log of 5, close parentheses, and you can see that I get 2. Okay? So that's the change of base one. So why don't you guys go ahead and try this one right here. Log of 17 base 3 equals what? Try it on your calculator right now. Make sure that you get it. I'm going to pause the video for it, and I'm going to tell you in just a few seconds. Awesome. So I'm going to talk you through logically beforehand. Watch this. So 3 squared equals 9, right? And 3 cubed equals 27. So I need 3 to something equaling 17. That's what I'm trying to find, right? I'm trying to find out what 3 to what power equals 17. Well, if squared is 9 and cubed is 27, I know that my answer better be somewhere between 2 and 3. And it's kind of close to in the middle between it, right? It's 8 above 9 and it's 10 below 7. But that better be my answer. So I'm using some dims. Some doesn't make sense. So like if I push this into my calculator like this, log 17 divided by log 3, and I hit enter, and I see this is 1.55. I'm like, well, that doesn't make sense. I know the number has to be between 2 and 3. So then I'll ask you, what did I do wrong? Think about it based on what was presented to you. Okay? You can pause it, think about it some more if you need to. Okay, so hopefully you said this, right? You went, oh, look, I forgot to close parentheses after the 17. Log 17, close parentheses, divided by log 3, close parentheses. I have to do the log of 17 divided by the log of its base. And now you can see I get 2.5789. That is between 2 and 3. That makes sense. Now I'm going to do this. Watch. I'm going to store this in x. Make sure that it works. So we're supposed to say that 3 raised to the x power, right? 3 raised to the x, that's supposed to be 17, right? If x is 2.57. And look at that, it is 17. Awesome. Okay, so I do want you to know that all 4 of these log laws work for natural logs too. So if I could do natural log of xy equals natural log of x plus natural log of y, natural log of x over y is equal to natural log of x minus natural log of y, and so on down all the way through, as long as they're all the same basis. And remember, right, the natural log of, say, 18, its implied base, right, its implied base is an e, even if we don't write it. Okay? So the last thing I'm going to do is I'm going to talk about decibels. So I gave you a big intro with the Richter scale, but now I'm going to talk about sound intensity. So what exactly is sound intensity? Well, it's measured with, I think it's watts per meter squared. It's a pretty funky number, but you guys know that you can get a dull sound like this, or a high-pitched sound, or I mean, just somebody screaming. Sorry. So if your parents are freaking out in the other room right now, tell them Mr. Bells is just talking to you about logarithms. If we were to say that we got this little formula right here. This is in your book, but they don't go into it in detail, so I want to give you a little bit more. Decibels, or the loudness in decibels based on sound intensity, is equal to 10 times the log of I over I sub O. And I sub O, this number 10 to the negative 12th, right? 0.00000, a whole bunch of zeros, right? And a 1, a bunch of zeros. I should put them all in there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Awesome. So 10 to the negative 12th, that many zeros and a 1. That is the lowest sound that a human can hear. Barely audible, right? Dogs can hear lower than that, humans can't. So the lowest sound a human can hear. So for instance, if we had something that had a sound intensity of 10 to the negative 4th compared to 10 to the negative 12th, if there was something like this, right? Then how would I figure out what that would be in decibels? And you would go just like this. You take, I'll go turn on, 10 raised to the negative 4th. Good deal. You hit down arrow, divided by 10 raised to the negative 12th. And I hit enter, and I get that, right? So that's, you can see it's 1, 2, 3, 4, 5, 6, 7, 8 zeros, or basically 8 factors of 10 bigger than that. Well, this thing says I take the log of that number, right? The log of that number. So I go log of that answer. And I get 8, and I times it by 10, and I get 80. So this sound right here, even though it's 100 million times more intense, we consider that 80 decibels. Okay? I'll just write it out, 80 decibels. Okay? Because it represents one factor in the decibel scale for every power of 10. There's 1 power 10, 2 powers 3, 4, 5, 6, 7, 8. Good deal? So there's a question on your homework that says that a whale can make a sound that is 100, nope, I think it's 1,000,000 times. 1,000,000 times louder than what a human can make in terms of sound intensity. Awesome. So then what would that be equivalent? Well, you could go ahead and find out what the thing is for this, but we know that this just becomes this. So in order to figure out the decibels for that difference, I would do 10 times the log of 1,000,000. And you'll see that I get 60 on that. So that is, that is one of your homework questions. Hopefully that helps. Practice your log laws. Remember that expanding means you're writing them out longer. Condensing means that you're shrinking them in. So for instance, an example. So if I had the log of 2x squared y cubed like this, and I wanted to rewrite this out in expanded form, I want to expand this thing. Then I know that I have the log of 2, that's from that one, right? And this is multiplication, right? Plus the log of x squared plus the log of y cubed. Then I can take these things and even write them down. So now it becomes the log of 2 plus 2 logs of x plus 3, what was that? 3 logs of y. So that would be in expansion. Now, if I had something like this, log of x squared over y cubed, I could rewrite it like this, 2 log x, because the 2 can come downstairs in the log, right? And this one's in the denominator spot, so minus 3 log y. That would be an example of expanding when you have a fraction. Okay, so hopefully this helps out. You can look in your textbook if you need some other stuff too. We should be good. Mr. Bells is out. Thanks.